Hello there, this is an Algebra 1 video. It is Chapter 9, Section 6, and today we'll be discussing analyzing functions with successive differences. This is also the last section that we'll be covering in this chapter, so dun dun dun, be prepared for a test soon, and very soon. Alright, so before we get going with successive differences, I want to just remind you of the three basic functions that we've talked about. A linear function, y equals mx plus b, what the graph looks like, very linear. It's a line, hence linear. Quadratic function, we have y equals ax squared plus bx plus c. Wrong color, sorry. And of course that looks like a parabola, which is an umbrella-shaped, U-shaped graph. And then we have, of course, the exponential function, y equals a times b to the x. Of course, b cannot equal 0, or b, sorry, has to be bigger than 0. And that function looks like this. All right? So one of the first things that we want to do in our example is to graph each set of ordered pairs and then determine whether the ordered pairs represent a linear function, a quadratic function, or an exponential function. All right? So to do that, we're going to go here. Let's see here. Negative 2, 5. So here's negative 1, negative 2, and 5. Negative those, positive 5 right about there. Negative 1, 2 is going to be negative 1, 2, 0, 1, 1, 2, and 2, 5. So one of the things that you can see is how the symmetry is working here with the points like that. So this to me appears to be, oops, why did it do that? This appears to me to be quadratic looking. Just like so. Alright, I barely missed a little dot there, but you get the point. Alrighty. This is part A, so it appears to look like it's quadratic. So now I'm going to go to our part B. Same thing, they want us to graph this little guy. So negative 2 is right here. And then 1/4, we're going by 1, so this is a half, so a fourth will be right about here. And then negative 1 and 1/2 is right here. And then 0, 1 is right here. 1, 2, and 2, 4. Now this is not going to be linear because the line won't go through those points, and it's not even going to be quadratic because then it's missing the other piece over here. So this looks like it's going to be exponential. And again, I want to make that like so. So this one's going to be exponential. And I forgot to put over here quadratico. Alrighty? So now we're going to let you try to determine for this guy. There is a part A and a part B, so we want you to, again, graph the set of ordered pairs and then determine whether it's representative of a linear function, quadratic function, or an exponential function. So there's part A, there's part B. And then we're going to go to our next example and our next topic. Okay, because like we said before, there are other ways to determine whether a function is linear, quadratic, or exponential. And one of those ways is using patterns and successive differences. And successive differences is basically just when you take the differences of the y values in succession. And if you do that twice, then they become second differences. This might sound kind of complicated to you right now, but I'll explain it in our example. But the differences of successive y values are called first differences, okay? The differences of successive first differences are called second differences. And again, I know that's very wordy, so again, just make sure you write this down so that you can understand which one's which. But basically for a linear function, if you have the first differences all equal, that means it's a linear function. If the first differences are not equal, but the second differences are, then you have quadratic. And then the exponential is not even it is differences. It's not going to be subtraction differences, but it's going to be ratios of successive y values are equal. So if the ratios of successive y values are equal, and if that number, the r, is not 1, then it's going to be exponential. And again, we'll do this as an example so you can see, but here we are. It says, look for a pattern in each table of values to determine which kind of model best describes the data. So what you want to do is you want to find the differences in the y values. Okay, that's what we call first differences. So it's just successive y values just means that this is the first y value, this is the next one, the next one, the next. So successive, they're all in order. Okay, so to find the differences, you're going to go -3 minus a -8, which is a +8. And you're going to get 5. You do the same thing for the next two, and that means you're going to get 2 minus -3, or 2 plus 3, which is also 5. Then you're going to get 7 minus 2, which is 5. And then the last successive difference is 12 minus 7, which is also 5. So what you're seeing is that all of these values are the same. So these are called first differences, and they're all equal, and that means that it's linear. So our first example here is linear. Okay? Then we're going to do the same thing with part B. Part B, we're going to take 4 minus 8, which is going to give us -4. Then we're going to take 2 minus 4, which is going to give us -2. So you can already see that they're not the same. But we keep going, so we're going to go 1 minus 2 is -1. And then 0.5 minus 1 is -0.5. So they're not the same, but nonetheless, these are the first differences. Then we try doing the second differences. Second differences would be -2 minus -4, which is +2. And then here you would have -1 minus -2, which is 1. And again, they're not the same. But I'm going to keep finishing this off just so that you can see here. -0.5 minus -1 is 1 minus 7, you get 1/2, 0.5. Okay, so again, these are now called second differences. And so in this case, the first differences were the same. The second differences were the same. So now we can try the ratios and see if that works. So now we're going to try ratios. And ratios would be 4 divided by 8, which is 1/2. You would have 2 divided by 4, which is also 1/2. And now we're off to a better start. 1 divided by 2 is obviously 1/2. And then 0.5 divided by 1 is 0.5, which is the same thing as 1/2. So now you have that the ratios of successive y values are all the same. So in this case, it's exponential. Okay, exponential. Kind of wrote that word there a little weird like. Alrighty? Because they all had the same ratio and it wasn't 1. Alright, so now you're going to try this little guy. And then we're going to go to our next example, which is determine which kind of model best describes the data. Then write an equation for the function that models that data. So the first thing we want to do is find our first differences to see what kind of model it is. So we're going to say 18 minus 32, 8 minus 18, 2 minus 8, and 0 minus 2. So 18 minus 32 is going to be -14. 8 minus 18 is going to be -10. So they're not going to be first differences the same, but we're going to keep going in hopes that maybe the second differences will be the same. So now for the second differences, we have -10 minus -14, which is 4. -6 minus -10, which is 4. And -2 minus -6, which is also 4. So in this case, we didn't get first differences the same, but we got second differences the same. So this is going to be a parabola, and it's going to be y equals ax squared. And I know that because it has 0, 0 as one of its points there. So it's going to be a form of y equals ax squared. So now I can just use one of the points that I have here, and I can determine what the a value is, so I can find the equation. So I'm just going to go ahead and use this point here. So the x coordinate is -2, the y coordinate is 8. So we'll put in the y spot 8 equals a times x, and the x spot we'll put -2. And then I'm just going to solve for a. So this is 8 equals -2 times -2 is +4, so 4a. We divide by 4, and it turns out that a equals 2. Now that I know that a equals 2, I can plug it into my original formula there, and my formula or equation for the function will be y equals 2x squared. This is the equation that models the data. So now we're going to ask you to do the same thing with these two examples, and then we will go to our last example. Oh, word problem, yay, they're your favorite, I know. The table shows the number of book club members for 4 consecutive years. Determine which model best represents the data, then write a function that models the data. So we need to find our differences here. So we're going to do 10 minus 5, which is 5. 20 minus 10. Actually, I already noticed the pattern, so I'm going to abandon this idea. And you're okay to do that if you see a pattern right away. One thing I noticed is that this looks very exponential because I'm looking at the ratios, and if we actually use ratios instead of differences this time, we'll go 10 divided by 5 is 2, and then 20 divided by 10 is 2, and 40 divided by 20 is 2, and 80 divided by 40 is also 2. So I noticed that as I was doing the differences, and then I abandoned that, and that's okay. You don't want to do work that you don't necessarily have to do if you can avoid it. So it turns out that in this case, I know now that it's exponential, and because it's exponential, it's going to have a model of y equals a times b to the x power. And I know that my b value is 2 because that's the ratio that I got that was over here. So I know that the b value is 2. So y equals a times 2 to the x. And now I can do what I did in the previous example, which is to pick one of the points for my x and y, and then find what a is. So I'm going to go ahead and pick the first point, why not 0 and 5, and my y value is 5, and I don't know what my a value is yet, and then 2 to the 0 power, because x is 0. And we learned a while back that anything to the 0 power is 1, so that means that this is just 1. 1 times a is a, and therefore a equals 5. So if a equals 5, I can now finish off my equation by saying that y equals 5 times 2 to the x power. And that will be the equation or the function that models my data. Alrighty, so awesome. So now you will try this do-it-yourself question. And once you have completed this do-it-yourself question, you will have completed your notes for this lesson. And I will see you in class. And thanks for watching.